Lectures 7 through 10 are now up. Okay, they're posted, and they also contain an outline of what we're going to start talking about today. That's electric circuits. They also contain, in the last 3 or 4 pages, a sample exam number 1, which is of a level that I would expect you to be able to complete in the 75 minutes that you will have. So, you might like to give yourself a little test, maybe at the weekend or early next week, by sitting down and on your own doing that. I recommend that that one you would do on your own, just to check that you are up on things yourself. I would recommend for the trial exam that you perhaps at least begin by working in teams. Okay? That's a very good way of, first of all, learning to articulate problems that you're having with understanding of the material. I'd like to remind you also that I'll be in at 7:15 tomorrow morning in Math-254. I'll be in at 8 o'clock on Thursday morning in the same venue, Math-254. And you're all very welcome to come along. You don't actually have to have questions, but because several people come along, some people have a question or two, and then that triggers questions that you may have. But you may also have specific questions or specific problems on the trial exam or on the graded homework number 4, which you'll receive tomorrow or so, whatever, and you're very welcome to come along to those sessions to get some help. I also recommend that you try to go to your TA's office hours on a regular basis. Right. So, today, first of all, let me review what essentially you will be expected to know for exam number 1. If you're following in the book, it's essentially chapters 1, 2, and 3, although I only examine you on the material that I have covered in class and that is covered in my notes. There are a few extra things in the chapters 1, 2, and 3, which are interesting, but not examinable for you for this part of the course. So what do you need to know? You need to know what a differential equation is, what an ordinary differential equation is, the various types, ordinary differential equations, system of ordinary differential equations, and the various classifications, order of the equation, whether it's linear or nonlinear, autonomous or non-autonomous. Then it's very important to know what the methods for solving these equations are. Now, we have only covered 4 methods in class, and that's all we will cover for the term, for first-order equations. There are other tricks, there's a few other methods, but you so rarely meet them that it's much better to know the methods that you will use often, to know those very well. And those are separable, direction fields, graphing the right-hand side of 3,1 there if the f does not depend on the independent variable x, and finally the method for solving linear equations. So they are the methods. Then we talked a little bit about difference equations. I'm going to talk a little bit more about them this morning. And in particular, we will learn about the ideas behind setting up numerical algorithms in order to simulate equations such as 3-1, simulate the solutions. Finally, applications. Very important. Very important. And the applications that I expect you to know are to the mixing problems, cooling problems, radioactive decay, population dynamics, and then two more that you're going to begin to meet this guy today, and you'll get the last part of the lecture next Thursday on electric circuits, and then bodies falling under the influence of gravity and friction. Right? How many people here are going to do mechanical engineering? Are you beginning to take a course now on fluid flows?
Not yet.
Not yet. Okay. When you do, you're going to meet a fellow called the Reynolds number. The Reynolds number. I want you to look up, before we get to the bodies falling under the influences of gravity and friction, I want you to look up what is the Reynolds number and what does it mean. Because we're going to be talking about throwing baseballs, things like that. And so the law, the friction law, you know, how the friction force depends upon the velocity of motion, the instantaneous velocity of the ball, is very important. We're going to find for most cases it's proportional to the square of the velocity. It's only very small things like little red blood cells moving in very small capillaries. Is the friction just proportional to the viscosity, to the velocity itself? Another example where it is just proportional to the velocity is the little water droplets, tiny little water droplets that are the nuclei of eventual raindrops in clouds. These things are circulating around in the great convective motion going on in a cloud, but they're very, very tiny, at least before they start coagulating with each other and condensing with each other. They're actually 25 microns or so. And then in those cases, actually, the friction forces they feel are also proportional just to the velocity. But for most everyday circumstances, like hitting a tennis ball or throwing a baseball or jumping out of an aeroplane. How many people here have jumped out of an aeroplane? Okay. Did you have a parachute? Yeah. In the book, it actually treats the jumping out of an aeroplane problem as if the friction is proportional to velocity. That's nonsense. When you jump out of an aeroplane, both when you're in free fall and even after your chute opens, the friction force is proportional to, roughly, velocity squared. So we'll learn why that's the case, and we'll learn to solve the equations for the velocity and the position of the particular body that's doing the falling. Very good. So difference equations. Difference equations. We'll write them. So difference equations are about a discrete relation between the values of a function at discrete points. And so the value of an object at position n plus r could be written as a function of it at the immediately preceding point, and maybe all the way down to yn, and it could also depend upon n itself. So this is the analog, as it were, of this differential equation. Actually, that's a first order equation. This is higher order at the moment, and I'll explain that right now. So again, we have the notion of type and classification. So the first classification is order. The order is the number of points which are connected with each other. Here we have n plus r connected with the value at n plus r minus 1 all the way down to n. Okay, actually there are r plus 1 particular points here, but we say this is of order r. This would be of order r. Then we ask, is it linear or nonlinear? And the definition is exactly the same as for differential equations. If f is a linear combination of yn plus r minus 1 all the way down to yn and 1, then 3, 4 is linear. If not, it's nonlinear. Next notion, autonomous. Or non-autonomous. If f does not depend explicitly on n, that's the running independent variable, it's the analog of x up here, then we say 3, 4 is autonomous. Right, so now let's actually look at lots of examples. Right, remember the Euler algorithm. For dy by dx equals y. The general Euler algorithm, the Euler for right-hand side f of x, y, was yn plus 1 was yn plus h times f of xn yn. We'll come back and I'll remind you how we derived that shortly. But now I'm just going to use it here to illustrate the various types of equations. So, this guy, if you remember, for Euler, for dy by dx is just y. You see here, yn plus 1 is yn plus h times. Now the f, if the f right-hand side is just y, f at xn and yn is just simply yn. So it's h times yn. So this is the Euler algorithm for this. So what is the order of this equation? What is the order? What is the order? 1 is correct. So the order is 1. Is it linear or nonlinear? Is the equation just a linear combination of the values of y at these various points? It's linear. Is it autonomous or non-autonomous? It's autonomous, because there's no n explicitly in the equation. How about this equation? yn plus 2 minus 2yn plus yn minus 1 plus h squared yn equals n plus 3. What is the order, first of all? Second, 2. So the order is 2. Is it linear or nonlinear? It's linear because the equation is a linear combination of, oh sorry, that should have been 1, sorry. But let's go back. There are 3 guys interconnected here, n plus 1, n and n minus 1. The order is 1 less than the number of points connected by the difference equation. It's second order, therefore. It's linear because it's a linear combination of yn plus 1. The coefficient of yn is minus 2 plus h squared. The coefficient of yn minus 1 is 1. And the coefficient of 1 is n plus 3. So it's linear. Is it autonomous or non-autonomous? It's non-autonomous because the coefficient here depends upon the independent variable, the running integer n. Another example. yn plus 1 is mu times yn times 1 minus yn. This is a very famous equation. It's the discrete analog of what we had called the logistic equation, which describes population growth. So this describes population growth in a year-to-year basis. Instead of considering the population y as a function of an independent variable t, which is continuous, we're thinking of just logging the population, say, on the 1st of January every year, and we get a discrete set of values of the population. The population at 2013, January the 1st, is y1. 2014, January 1st, is y2, and so on and so forth. This is a very famous equation. You might look it up in Google, the logistic equation, because it has absolutely fascinating properties. It's also discussed in the last chapter, the last section rather, of chapter 3 in the book. There's a fellow called Robert May who made a whole career, well, he didn't quite, but he started a career very well out of this equation in the mid-70s. He's now actually Lord May. You know, the British, instead of paying you, what they do to reward you, they give you titles. It's the most wonderful colonial system. You know, for the most part, well, in Arabia and in Ireland, there was an exception a bit, but they were able to control vast empire by just handing out sirs and lordships and things like that. You know, we could learn a lot from them. They also actually, I have to hand it to them, they have a splendid sense of humor. Yes, yes. Yes, no, the sense of the ridiculous of the British is second to none. Second to none. I mean, you've all seen episodes of Monty Python, right? Huh? And before that, there was Beyond the Fringe. You remember? Is Dudley Edwards, Peter Cook, are those guys too old for you? Yeah, a little bit. Well, look up Beyond the Fringe. These are, yeah. And, yeah. And then in the 50s, there was this wonderful thing called The Goon Show. Anybody ever heard of The Goon Show? Wonderful stuff. Wonderful stuff. Anyway, where am I? How did I get caught up in all this? Yes, I was talking about Lord May, Robert May. He actually became the scientific advisor. I think he may still be the scientific advisor in England at the moment, or in Britain at the moment. Anyway, this logistic equation has fantastic properties. One of the properties is that it depends on this parameter mu. If mu is less than 1 in magnitude, if you compute the solutions successively, I mean, start off with, say, y1 equals, say, 1, and then just compute y2 from this equation, and then compute y3, etc., etc., those set of values will converge to 0. When mu is greater than 1, and bit less than 3, they converge to another fixed point, which isn't 0. Something like 1 minus 1 over mu. When mu gets to be greater than 3, fascinating things happen. That solution becomes unstable, and the solution tends to jump between two values. The y1 will go to one value, the y2 to another, the y3 back to the same value as y1, and the y4 back to the same value as y2. And so it'll keep leaping between these two values as you march forward in n. That's called a period doubling transition. And actually these are seen quite frequently in nature. As you stress a system more and more, the system, instead of having a equilibrium, which is time independent, starts leaping about from one value to another in a periodic way. Then if you increase the mu a little further, you go to period 4. So y1 will go to one value, y2 to another, y3 to another, y4, and then y5 will be back to the y1 value. So it hops about between the 4 values. And then as the mu increases a little bit more, it'll hop again to 8 and so forth. And then at a certain value, it'll actually become completely chaotic. It'll be jumping all over the place. So it's a wonderful example of the transition from a kind of ordered motion to a chaotic motion as this stress parameter, as this parameter mu, is increased. So there's a nice picture in the book of the way it hops about as mu increases. So what's the order of this equation? One, because it connects just the value of y at 2 points, n plus 1 and n. And so the order is 1 less than that. Is it linear or nonlinear? Nonlinear, because it contains a yn squared. Is it autonomous or non-autonomous? It's autonomous. Now, another example. And this time, you guys get to do some computing. Now, what's the order of this difference equation? Second, right? Is it linear or nonlinear? Autonomous or non-autonomous? Okay. Now, I'm going to give you two starting values. At n, I'm going to give you y0 equals 1, y1 equals 1. I want you to compute y2, y3, y4, etc. So would you all do that? Now, Toshi, what did you find? I want you to compute. If y0 is 1, y1 is 1, what's y2? Right? Still computing, okay. Well, let's compute them. So what's y2? 2, right. y2 is 2. What's y3? 3. What's y4? 5. What's y5? 8. What's y6? What's y7? What? 21. What's y8? What's y9? Toshi, does this strike any chord with you? What were you so good at last time? What did you count for me? What did you count? The sunflower, the spirals, the number of spirals in this family. Each seed here in the center of the sunflower lies on one of two families of spirals. One going clockwise and the other anti-clockwise. And the number of spirals in the anti-clockwise direction is 55, and the number of spirals in the clockwise direction is 34. Is that an accident? No, it isn't. But it's a fact that has been known for 400 years, but it's only in the last decade or so that real rational scientific explanations for this phenomenon have been given. Now, if you started off with y0 is 1 and y1 is 3, what would the sequence be then? Supposing I start off with another set. y0 equals 1, y1 equals 3. What's the next one? 4. What's the next one after that? What's the next one after that? And the next one after that? Okay, next one. And so on. This is called the Lucas sequence. It is a Fibonacci sequence. The Fibonacci sequence, there's many Fibonacci sequences. What's important is the rule. The Fibonacci rule says that to get the next number, you just add the last two. So depending on where you start, you could get lots of different sequences. They all have a very, very interesting property. If I define yn plus 1 over yn, the ratio of two successive terms to be xn plus 1, then if I divide across this equation by yn, I get yn plus 1 over yn, that's xn plus 1, equals, dividing yn into this gives me 1, plus yn minus 1 divided by yn, which is 1 over what we call xn. xn would be yn over yn minus 1. yn minus 1 over yn would be 1 over xn. Now, let's compute these guys. These guys, if I start off with x1 is the ratio of the first two, if x1 is 1, x2 is going to be 2, and so on. x3 is going to be what? 3 halves. x4 is going to be what? 5 thirds. x5 is going to be 8 fifths. So on. The limit of the ratio of two numbers in any Fibonacci sequence tends to 1.62, which is actually 1 plus root 5 over 2. This is a very famous number. It's called the golden number. Anybody interested in architecture? Yes. Where does this ratio, this golden mean, come into design? And
it's stuff that's organized and sized in the golden ratio is generally pleasing to the eye.
Yes.
In a lot of Greek and Roman architecture.
Absolutely. Well done. Absolutely correct. If the vertical height of a wall to the horizontal length, if that's in this ratio, or actually, sorry, the other way around, the horizontal to the vertical, if that's in this ratio of about 1.62, it is for some reason pleasing to the eye. And do we understand the reason for it? No. No. At least I don't. If anybody can enlighten me, it'd be terrific. This is a wonderful open question. Why is it? First of all, I'm not sure how carefully a scientific study has been done to determine if what you suggested is absolutely true, or if it's true, amongst a set of artists, or but it generally is conceded to be, people think it's true. If it is true, then it is worthy of explanation. It's important to understand it. Somehow, in our minds, we have natural mathematical structures that the beauty somehow of this mathematical language is somehow hardwired. And, this is a question I've always been interested in. By the way, if you're interested in phyllotaxis. Phyllotaxis means the arrangement of flowers or seeds or whatever on the heads of plants. It's a fascinating subject, and if you have a spare few hours, you might like to read a little bit about it. And then when you go to walk out in the desert, you'll see lots of examples of spiral phyllotaxis. And the other thing is we get a lot of whorl structures. For instance, like you get 2 leaves on a stem being like this, and the next 2 leaves, the next 2 leaves which were born after these 2 leaves would be at right angles, and so on, and they go backwards and forwards like that. That's called a decussate. But sometimes you'll see 3. There'll be 3 leaves coming from the one spot on the stem, okay, and they're at 120 degrees apart, and then the next set of 3 leaves would be twisted by 60 from each of those, and it goes on. So for some reason, nature likes to choose these various structures. All these things are made, by the way, at the growth tip of a plant. I mean, the leaves, when they grow a bit and they grow down, the stem grows through them, as it were, and leaves the leaves behind. But actually, the formation of everything is at the growth tip. And so understanding the processes at the growth tip are very important. Now, back to the dull subject of differential equations, or difference equations. Let's take a look now at, I want to just remind you about Euler, and ask you about how we might improve on Euler. If I may remind you, Euler comes from what? What we're interested in is the following. If I integrate this equation up here, okay, starting from the point 0, I get y of x equals y of x0 plus the integral from x up to x0, x0 up to x of fc y of c dc. That's exact. I just integrated that equation. Now, I don't know, of course, what the solution y of x, y of c, between x0 and x, I don't know what that is. That's the solution to the differential equation. But assuming that I have a solution, then this is a true statement. Now, how is it that you might seek, yes?
To clarify, what is the symbol that you used inside the f there?
That's the running variable of integration. Okay? I don't want to use x because I'm integrating up to x. Let me draw a picture. So here's the x-axis. Here is x0. Here is x1. This is a distance h away, x0 plus h. Up here is x capital N, which is x0 plus capital N times h. So in other words, I've split the axis, and here's x little n, and here's x little n plus 1. I split it up into intervals, each of length h. Now imagine the solution. This is the y0 given to you. The y1 might be here, so the solution might be something like this. So this would be y1. This would be the point yn. This would be the point yn plus 1. And this here would be the point yn, this height here. Okay, so I've just drawn a graph of the solution between x0 and x capital N. Now I'm going to draw a graph of what f would look like. Okay, if I know y of x, here it is, then the f, say, would look something like this. This is xn. This is the x little n plus 1. The f would look something like this. This would be f at x0, y0, that height here. So this is the graph now of f of x and y of x. So it's a function of x. I draw it imagining I know the solution y of x. So f of x and y becomes just a function of x. And so it'll look something like this, like that. Right. Now, supposing I want to approximate. You see, from this, if I want to integrate yn plus 1, would be yn plus the integral from xn to xn plus 1 of f of c, y of c, dxc. In other words, I just put this at xn plus 1. I put it at xn. I subtract those two expressions. One expression, they each have y of x0 in them. That'll cancel. One expression will be x0 to xn. The next expression will be x0 to xn plus 1. When I subtract, I'll get from xn to xn plus 1. Question?
So that interval notation that you write on the right side, all that's saying is you're just integrating between
Yeah.
two 2 points
Yeah,
of the function.
exactly. That's all I'm doing. And in a sense, it's content. I mean, it's true, but it doesn't enlighten you because you don't know what the y is in between or anywhere else. Question.
Yeah, I'm sorry, I had some doubt for a second. What is the function there that you are integrating the f?
This is the function f. I take the solution y of x. I plug it into the f value I have, and I plot this as a function of x. And that's its shape. Now, what does this mean? Don't zone out on me again. I want you to tell me, what does that thing, what does that represent in terms of this graph?
The difference in height between 2 points?
No. If I just take a function of x, and I integrate it between a and b. So here's the graph of f of x. I integrate it between a and b. What does the integral of a to b of f of x dx, what does it represent geometrically? Very good. It's the area. So this guy is this area. Okay? That's what this guy is. Right? Now, somebody suggest, how might I, if this is a small distance here, this is h, which is 0.01 or something like that, how might I approximate that area? How might I approximate that area? This sort of goes back to the sort of calculus. Yes, exactly. You could approximate it. You could say the integral from xn to xn plus 1 of f of c, y of c dc. We could represent it as this. So let me draw this again. So here's my function f of x and y of x. It's just a function of x. Here is xn plus 1, xn. Beside it is xn plus 1. They're a distance h apart. This gentleman here has said, okay, here's the area. I'm going to actually approximate it by taking this value here, which is f at xn and yn, that's that height, and multiplying it. So I'm going to approximate this area under this curve by that rectangular area. So what's that rectangular area? Right, h times f at xn, yn. So this would be then, I'd have yn plus 1 equals yn plus h times fxn yn. What did we call that scheme? Euler. That was Euler. Okay. Could anybody suggest a different way? Well, actually, let me ask another question before we do that. We could ask the question, we could say, what roughly is the size in terms of h of that little mistake, the error? Yes?
Would you like subtract the over approximation by the under approximation?
You could. The over approximation you're saying, now let's take it here and come back to here and get that one. Yes, yes. Yes, that would be the right hand one. But roughly, what is this area going to be in terms of h? Yes. Right. It'd be roughly, if f is fairly smooth, if it doesn't get very steep, this guy is of the order of h. This is h. So the area is going to be roughly h, if I multiply h by h squared. So the area, or the error per step will be h squared. But now I have n, capital N steps, where capital NH is x. So the cumulative error would be h. Okay? So the step-by-step error, step error is h squared. The cumulative error is h. Question?
H squared over 2.
Well, it would. It would have a factor in front. Yeah. You're absolutely right. It'll be actually more complicated because it's not a perfect triangle. Now, we could try another way of approximating this. Now, we could do, as you suggested, we could take this rectangle here, but that will make of the same order of a mistake. What else could we do? The midpoint. Excellent idea. So we could do midpoint. And that would say h and f at xn plus h over 2. And then it'll be y at xn plus h over 2. Okay, this is called the midpoint. Now the trouble is, of course, we don't keep this. We'd have to have an algorithm for the midpoint y. But if you did that, it's a good idea. If you did that, actually, then it's like taking this triangle. What would be the error then, actually? The error per step. Actually, it's a little bit harder to see. The error, so for midpoint, this is midpoint. The step error is h cubed, and the cumulative error is h squared. So you're getting better, you see. H is small. You get a much better cumulative error if you use this. But the trouble with the midpoint is I have to then get the y values at the half points. Can anybody think, what do we use? Yes. Trapezoid. Absolutely. The trapezoid. What we'd do is we draw a straight line between those two, and then the blue area is h times f at xn yn plus f at xn plus 1 yn plus 1 over 2. Okay? So that's trapezoid. So yn plus 1 is yn plus h times f xn, well, h over 2 okay. Now, can you tell me why this is less desirable than Euler? It's certainly better in the sense that his cumulative error will also be order h cubed. His stepwise error will be of order h cubed. His cumulative error will be h squared. But what's not so pleasant about this formula? Yes?
That you need to know y plus 1.
The trouble is the yn plus 1 was given explicitly in terms of the last point here, but now it's implicit because it's contained here. So you actually just do a little adjustment and you write it as this: h over 2 fxn yn plus fxn plus 1, and then you replace the yn plus 1 by the Euler expression. And this is called, so this is trapezoid. And when you take out that yn plus 1 and put it in terms of yn, this is called improved Euler. All right. So you remember in calculus in 129, you learned how to approximate integrals. What's the next one up? After midpoint and trapezoid, Simpson's rule. Okay? Well, essentially, Simpson's rule starts becoming, in the differential equation, the Runge-Kutta. So, in fact, by taking various combinations in the correct way, you can finally find a scheme whose stepwise error is h to the 5th, and its cumulative error would be h to the 4th. That's called RK4 in your scheme of integrating things in your program, your software program. I think the software program has a default setting Euler or midpoint Euler or something like that, and I think the h was 0.3. But you can reset that and use Runge-Kutta at 0.1, something like that. You get very accurate behaviors then. So do you get the idea, actually, to convert these differential equations into numerical algorithms. Essentially, you integrate this formally to get this expression here. Then you have the stepwise thing here, which is gotten by putting x equal to xn plus 1, and then equal to xn, and that'll be yn plus 1 and yn. Subtract the two things, you get this. And then it comes down to a matter of how you're going to approximate that. But how you approximate that is exactly the way you approximate areas under curves that you learned in calculus. Now, I never remember what the Simpson's rule is. I mean, it's too complicated for me. So, but in any event, the program has that algorithm built in. What I want you to understand is, A, the idea behind making these approximations, these algorithms, and the importance of finding a cumulative error which is as high a power of h as is convenient. Because that means essentially you can take quite big steps. If you take h equal 1/10 or even 1/2, h to the 4th is 1 over 16. So you could take fairly huge steps, and the error that you're going to get in your scheme for the solution of the equation isn't too bad. Now, somebody had a question. Yes?
Yes. Why again did the cumulative error go down by 1?
All right. If the stepwise error is h to the, say, cubed, then to get up to a point x, which is capital N times h, there'll be n such errors, right? The cumulative error will be n times this. N times h, that's a finite number now, that's x, times h squared. So that's a finite number times h squared. So the cumulative error is just the effect of adding up capital N errors, each making the error h cubed. Now, there are lots of constants in front, and the constants depend upon how much of a slope, you know, the shape of the curve f of x and y of x. For instance, if we start trying to do these methods for an f that starts looking like this, like 1 over y minus 1, or 1 over 1 minus y, then we're going to get into a bit of trouble when we're here, because these approximations to the area under the curve get worse and worse as you approach this singular point. Right. Okay. We will meet difference equations again. I'm not going to introduce the method for solving them now. We actually used a method to solve Euler when we looked at the example dy by dx is y. But we'll meet them again. But I just want you to know the basic idea of setting up the algorithm and the various types and classifications for difference equations. Yes, question?
Would you like me to know how to prove the trapezoid function, like dig through?
Would you be expected to know that?
Yeah.
I would expect if you were having to solve a problem, and you know, you could go look it up, that you'd know the idea and the exact form of it. You might have to look up in a book. I don't expect you to remember that in an exam, if that's your question. Yes?
So, will some of the formulas be given to us on the test?
Will some of the formulae?
Will they be like given like on the test as like?
I've told you, any complicated formulae will probably be on a list of useful information. Okay? I don't want you to get hung up remembering particular formulae. But generally speaking, at the end of the course, I'll be handing out in about a week a list of things I expect you to know, trigonometric identities, integration rules and that sort of thing. I expect by the end of the term you're going to be a whiz at all of them. But we'll see. Right. The next thing I'm going to cover now is electric circuits. Yes? I'm sorry.
I follow this. I'm just a little confused as to what we're going to be, like what we would encounter on a test. Should we be able to take differential equations and put them into this yn plus 1 formula?
Well, if that was going to be on an exam, and an exam question, I'd probably lead you by the hand through various steps.
And one more thing, sorry, it's a bit late, but I was just wondering, on number 4 there, why is that second order when on the right-hand side only 2 y to the n's are linked together?
No, it relates the y value at 3 successive points.
Then why is the one above it first order if there's...
Because it only relates 2 points, n plus 1 and n. Right. In general, if you're connected through, well, I've taken it off here. If you've r points, r plus 1 points connected, that's order r. Okay. Now I'm going to start on a few ideas about electric circuits, and next day I'll teach you how to write down the equations describing the currents flowing around any network of circuits. But let's begin by talking about electric currents. Okay. Where actually do you see some evidence of electric currents in engineering contexts or in the atmosphere or in science in general? How many of you have seen the aurora borealis? Where were you when you saw it?
I saw a video.
Ah, that's okay. Probably came through much better and much cheaper way of seeing it. Yes.
I was up in Coldfoot, Alaska.
In where?
Alaska.
Yes. Whereabouts?
Coldfoot. So
That's.
down south of like
I see. What colors did you see?
red, orange, green.
Well, lovely. Fantastic. Yeah. Do you know what causes it?
Electrons in the atmosphere getting excited or something.
Right. Charged particles in the where do they come from, these charged particles? The sun. What's the medium? What name do we give the medium that carries these particles from the sun to the earth? Yeah?
The medium that carries the charged particles from the sun to the earth, we call that coronal mass ejection.
Right, or solar wind. Solar wind. So why did you have to go to Alaska, do you think, to see this? Why didn't you see it in Tucson? Why did they go to did they like the poles? That's where they all go for the winter, like. Right. The Earth's magnetic field essentially is a dipole, and the field lines look like this. So actually they protect us because the charged particles, instead of coming through and bombarding us here, they get trapped around these magnetic field lines and spiral and bounce actually backwards and forwards between the two poles where the strong components of the magnetic field actually enter the Earth. So that's why these particles come crashing into the atmosphere both near the North Pole and the South Pole. And so essentially you have a plasma. You have this soup of charged particles, electrons and what do you call positively charged particles? Ions or protons, yeah.
Yeah, I was just going to ask, it happens on both poles, it doesn't just happen to just the positive pole?
Right, it happens on both poles, yes. Because the charged particles actually bounce backwards and forwards between the two. Okay, so in plasmas are very much heated, essentially gases heated so that essentially the molecular structure, the molecules split up a bit. They toss off their some electrons and become positively charged, and then you have the electrons wandering around. So you have this soup of electrons and ions. Now it's very important, of course, I mean, in thermonuclear fusion, which we'd like to simulate, we'd like to kind of keep this soup of very hot stuff in some nice container so that these hydrogen atoms, deuterium atoms, can bump into each other often enough and make little helium atoms and then give off a little bit of extra energy. They lose a little bit of mass in that process and give off some extra energy. And it will be wonderful whenever we perfect this means by which the sun produces its energy. Now, it's a ways off yet. Don't buy shares quite yet, but it's our ultimate hope. So plasmas, dealing with plasmas, is very, very important. Very important. Where else do we see, now let's, in chemistry, in battery chemistry, where do we sort of see another example of charged things wandering around? Yes?
Isn't it like a gradient, like the ion gradient?
Yeah. What happens if you put salt in say a fluid like water? It does split up a bit, doesn't it? In NaCl gets the Na part. You see, the chlorine has 7 electrons in its outer shell, and it would like to grab the one extra one in the sodium's extra shell, pull it into it, so it becomes slightly negatively charged, whereas the sodium then becomes positively charged. And then, supposing you put an anode and a cathode, then the chlorine will move to the one side, and what do we call them? Electrolytic solutions, right? Electrolytes, right? Now, what's another example, much more mundane? What's another very mundane example of charges? Yes, correct. So, what? Wires, conducting materials, where you have electrons running along wires. So actually, the first thing is, so what moves? What moves? Yeah? What moves?
The electrons.
Yes, electric charges. I mean, there may be ions as well. I mean, in wires, it's mostly electrons. Yeah. So charges. And what's our unit of charge? Do you remember from physics? Coulomb. Your unit of charge is a coulomb. So we measure in coulombs. Now, does anybody know the electron? What is the charge on an electron? What's the charge? Yes, the charge on an electron. Yes.
About 1.6 times 10 to the negative 19 coulombs.
About that. Could you be more accurate? That's terrific. How did you know that? Yes, you got everything right except the most important part. Right. So what flows? Oh, did I? Yes, 19 is correct. So what flows? What's the stuff that, what do we call the flow? Current. Current. How do we measure current? Amps. Yeah. Amps. And amps are coulombs per second. So what's the amperage, say, in the regular electric supply? Roughly what? How many amps? What do you set your, what do you call them, fuses at, roughly? 24 sometimes, yeah, but usually, what, 15? So of the order of 10 amps. How many electrons have to flow per second to get 10 amps? A whole bunch. 10 to the 20. So that little wire, things are flying along in it. Huh? Yeah. What pushes? What pushes? I mean, how? Yes. EMF, voltage. Okay? Now there's a nice fluid analogy. You think of a pipe. Think of a pipe. And down this pipe, so we have a slug, say we'll call it dx in length. And the density, this is density per unit length. So actually the mass, rho dx, the mass of this slug, that's like the charge. So rho times dx by dt is like the current. So this is the momentum. The other is mass. The mass is like the charge, the momentum is like the current. And what's the analog for voltage? Somebody said it already, I think. What pushes? Pressure. So pressure pushes. So you have more pressure here than here. PA, PB, the stuff will flow that way. Okay? So there is a sort of a fairly precise analogy between current flow and fluid flow. There's a convention. Now we have to learn the convention. Maybe I'll talk about the convention next day. It's just the direction of current, what we call a positive current. Because you see, for the most part in wires, it's electrons running this way. So the electrons, because they're negatively charged, run counter to the direction we say the current flows. Okay? So now, what we're going to learn, we're going to start next day. We're going to learn about the electric circuit ingredients. What are the main ingredients in electric circuits? Resistance, capacitance, inductance, and a source of EMF.